Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about epsilon NFAs, or if you want to think about them fully, it's a non-deterministic finite automaton or automatons with epsilon transitions. Sometimes people call these epsilon moves, the epsilon transition. It's a cuter name. I like it. It's kind of cute. So we're talking about NFAs with so-called epsilon moves. So I wanted to give you the formal definition of an epsilon NFA first, because last day I was trying to motivate you to why you would want to consider having this extra feature for an NFA. So last time I talked about this idea that we could build an NFA that allows you to transition on epsilon, the empty string. So here's the definition. It's really simple. I didn't want to give you a whole list of the parameters all over again. So it's essentially the NFA, except I changed the transition function just slightly. What I do is instead of having it where it's a state, then a input symbol, and then I get a state, instead it's a state, I get a state, and then I get an input symbol or epsilon, and then I get as output, I get an output, I get a, I'm pretty sure that's not that. It's supposed to be, it's supposed to be a set of, a state or a set of states? State or a set of states? I mostly wrote this here just to quiz you. It's a set of states. It's a set of states, right? That's the case with the NFAs, right? Perfect. I'm glad I caught some people on that. Good, good, good. Good. So we're going to go from having a state, an input symbol, or epsilon, and it gives me some set of states. Remember, this is the power set of the set of states. Perfect. See, I have to do that sometimes just to make sure everybody's on the right page. Okay, so the big thing I want you to take from this, two things. So they can occur either on an input symbol or epsilon, but I must stress that epsilon is not a part of the set of input symbols. It is not. It's a feature of the epsilon NFA. So just don't confuse this for just like the letter A or number 1 or something like that. Epsilon is the empty string. That's what it is. So just don't confuse the two. So where epsilon will creep up when we describe our epsilon NFAs are on transitions, like we did last time, or in the transition table, we'll put a column in for epsilon. So is everybody okay with this definition? So I'm just adding this feature to the NFA. So if there aren't any questions, I'm going to move on to a fun, I would consider this the thing that's going to carry this entire lecture. So it's going to start off with this kind of basic idea. And it should feel like something recursive to you. To determine how epsilon NFA process strings, we use the concept of a, I'll say N, of an epsilon closure, which I'll denote as E close, like this. So just informally, I'm gonna tell you what roughly it is. So informally, if I give you E close or epsilon close of Q with a given state, so this is a state Q. So if I give you a state, it returns all the states, that can be transitioned to by epsilon via or from state Q. So So you're going to look at like the epsilon like it's like a free ride to go from one state to another state. I could just take the epsilon transitions or these epsilon moves. So what eClose is going to do is it's going to give me all of the states that I will need if I were to just say take one of these free rides on an epsilon transition. So I need to define the epsilon closure for everybody formally. I'm going to do this inductively. You'll see why. So I'm going to define the epsilon closure more formally now. So remember, this is eClose of Q. I'm going to define the epsilon closure. So it's defined inductively. It's defined inductively as follows. So we're going to have a basis, and then we're going to have an induction part. So the basis for this is that if I tell you that I have the epsilon closure on a given state, the given state is in this set of states. So I'm saying state Q is in eClose or epsilon closure Q. So that you take as a given. So you know Q is definitely in eClose of Q or epsilon closure of Q. I'm going to use those terms synonymously just because epsilon is a little bit harder for me to pronounce very quickly. But it's not that big. Hopefully that's fine with everybody. It'll always be called this when I use it. Okay, so I'm going to say if P is in eClose Q, then so are all the states in the transition given state P on epsilon. So imagine I have some state P and it's in eClose of Q. Then you can guarantee that so if you put your finger, say if you look at the transition diagram, if you put your finger on the state and you see there's a transition on an epsilon, then every state that I can reach from P over a transition on epsilon is also in eClose of Q. So you're going to see it's kind of like a recursive algorithm of sorts. That's the way I like to think of it. It's like you keep repeatedly doing it. It's like I'm doing some sort of traversal over the epsilon edges. Which is what it is, if you think about a graph theoretically. I like to think of it that way. And I'm also going to make a remark. So it's just a remark, because sometimes it's handy to define the idea of the epsilon closure of a set of states. So I'm going to say, if we are given set S of states, then I'm going to tell you that the epsilon closure of the set S is just simply going to be the epsilon closure among all of its states. So Q in S, I'm just going to apply the epsilon closure, and I'm just going to lump them all together in one set. So I perform union over all of the states that are in S. That's all I mean. So it's just repeatedly applying epsilon closures on all the states that are in this set S. That's all I'm saying. And you just put them all together, you bucket them all up into one set. So are we okay with this definition? I'm going to do an example that should make this induction part a little bit more clear for everybody. I think we're all good. I think we're good. So I'm going to do an example. I'm going to draw a transition diagram, and then we're going to apply the epsilon closure to given states and also a set of states, just so we can get a flavor for what this looks like. Okay, so let's draw out so I'm going to draw a transition diagram. I'm also going to give its transition table just for the sake of completeness because we're going to use it later. So let me draw the following example. So I'm going to imagine I have a start state. I'm going to give it label, the state's going to be called 0. I'm going to have epsilon moves out of 0 to states 1 and 2. Then I'm going to have an epsilon move from 1 to state 3. So from state 1 to state 3. And I'm going to allow there to be a transition on a symbol A to state 4. I'm going to add another transition from 3 to 4 with the symbol B. So this is going to have input symbols A and B. I'm going to allow epsilon moves from 3 to this state I'm going to call 5, which is going to be a final state. And I'm also going to put an epsilon transition right here, or epsilon move. Then I'm going to have a self loop right here. It's just going to keep allowing me to read B's. So here's just a transition diagram with some epsilon transitions in it. I'm going to draw out the transition table because we're going to need it later. Well, it makes it easier. You don't necessarily need it. It's just, it makes things a little easier. Okay, I'm going to have my rows, one for each one of the states. 3, 4, 5. 5 is a final state. 0 is a start state. I'm going to add a column for epsilon, like I said. Then I'm going to have my input symbols A and B. So on epsilons, you'll see right here on state 0, I can go to state 1 or state 2 on an epsilon. So I'm going to write just states 1 and 2 like that. Remember, it's still an NFA, right? It's just that I have this epsilon. The way you can interpret this column is just like if I was transitioning on an A or a B. So likewise, if I am transitioning from 1 to 3, I can, so if I look at symbol 1 with epsilon, I can go to 3 from 1. Let's see what else. I'm pretty sure on 2, I can't go anywhere on an epsilon, so there's nothing there. It's empty. State 3, I can go to state 5, right? And on 4, I can also go to state 5. But on 5, nah, nothing on epsilon. Are we okay with this column? So it's just like what you were doing before. So you would treat epsilon like it's an input symbol, but remember, it is not. It's a feature of the epsilon NFA. But you'll very much treat it like it's an input symbol. Just because I need to make that distinguishing remark, because there's sigma, the alphabet that corresponds to the input symbols for the machine, and then there's epsilon. Epsilon is separate from that. Okay, so on A, 0, there's no transitions. On 1, there's none, I'm pretty sure. I believe there's a 4 here for 2, right? Yeah, it goes from 2 to 4 on A. Let's see. 3, nothing. Nothing. And I think nothing. Yeah, all that's nothing. It's not as exciting on the A and B side. So I'll just fill in B just for the sake of time. And I believe I need a 4 here on 3. Yeah, goes from 3 to 4. And I think I got nothing there for 4. And on 5, I can keep staying in 5 if I read a B. And this is my transition table for that epsilon NFA. Are we okay with the table? I was about to say trable for some reason. A table and the diagram. I think we're doing pretty good. Like I said, all I'm doing is I'm adding this extra feature. Now I want to do some epsilon closures on this right here, just so you can see. So let's do some examples, and maybe you can help me with this. So if I give you epsilon closure of 0, I'm going to do the first one myself, and then we'll kind of bum through each one. So if I read the epsilon closure on 0, you'll see that, okay, well, it better include itself, right? So 0 is definitely there. That's the basis. And then it tells me, okay, well, if there's a state in here, then so are all of the other states I can transition to on epsilons. So on epsilon, notice I can go to 1 or 2. So 1 and 2 are definitely in this set. So if I look at 1, okay, well, there's another epsilon transition. So notice I can go from 1 to 3. So 3 is indeed a part of this. Notice there's no state I can go to on an epsilon move from 2. So there's nothing there I can kind of explore. Notice that I have a 3 here, right? I could go on an epsilon move. So notice that I could go to 5. Notice I can't go to 4 because notice there's none of these transition on epsilon, right? So I can't reach 4. So it's very much just me like if I'm doing a graph traversal where I'm just looking at only the edges or arcs that have epsilon on them and where I'm starting off at 0. Is this everybody good with this example? Don't be shy. Don't be shy. Are we all good? Give me 2 thumbs up. I just need to see. I think we're good. Okay, so notice that in my definition of the epsilon closure, if, say I look at a state P, for example, like say if this was P, I would say that if P is in the epsilon closure of Q, Q would be 0 here, then so are all the states that I could transition to from this state on epsilon. So notice that I can go from 1 to 3 on an epsilon. I can go from 3 to 5 on epsilon, but notice that no edge, no directed edge or transition from 2 can get me to 4 because I require an A, not an epsilon. And on 3, notice that I don't have an epsilon transition that gets me to 4. I require a B from state 3. So that's why state 4 does not appear here. If you want to get, so there's kind of 2 ways you can think about it. That on epsilon moves, I can't get to state 4 directly from 0. I require more symbols. I need either an A or a B. However, a graph theoretic way you could think about this is that if I were to only interpret the graph from looking at epsilon edges, there is none that leads me to 4. There's no path. I would require to use an A or a B transition. Does that clarify that for you? Perfect. Okay, let's knock out some more, just so we can get a flavor for this. So the epsilon closure of 1. Can somebody tell me what the epsilon closure of 1 will be? So remember, I'm right here, and I want to know what the epsilon closure of 1 is then. I'll tell you first that, 1, 3, and 5. Perfect. Perfect. Everybody sees it, so I start off at 1. Notice that, okay, well, there's epsilon transition here, so I can get a 3. 3's in epsilon closure of 1, so I see an epsilon transition, it takes me to 5. Notice there's none others I can get. So I have 1, 3, 5. Okay, how about the epsilon closure of 2? Now, remember the basis part of the definition. So the epsilon closure of 2, it definitely has to contain 2, right? But notice there's no directed edges. I can leave from state 2 to go to a different state on epsilon, right? So it's just 2. So the first thing you should always remember with the epsilon closure is that if I give you the epsilon closure of a something, that something better appear in this set. But I want to do one with a set. I have actually in the notes, I've went through all of the states. So if you want to see all of them, so you can see that after class. I'm going to do an epsilon closure on 2 states. So I'm going to have a set containing states 2 and 5. So now the definition of the epsilon closure on a set of states is just simply going to be the union of the epsilon closure of 2 and the epsilon closure of 5. So remember, I computed the epsilon closure of 2. That's already just 2, right? And the epsilon closure of 5, what's the epsilon closure of 5? It's just 5, right? And it's a set containing 5. Because it's just state 5. And notice there's nowhere I could go. It's sort of stuck there. Other than state 5, that's it. So if I put this together, I get 2 and 5. Is everybody okay with the epsilon closure concept? Because we're going to use this. So if we're all okay with this, I'm going to give the extended transition function. You're going to get used to me having to define this extended transition function. Remember, this is just a formal way of me describing how the machine is going to process the string. So I'm going to define delta hat for epsilon NFAs as follows. So I'm going to have a basis and an induction part. Okay. So the first thing I should note, now you guys remember from when I defined the NFA's extended transition that I start off here, right? The start state. What's different now? What's different now? Can somebody point it out for me? What's different about the epsilon NFA than the NFA? What is the start state? Is it just this? Yeah, so you could start here, but remember, the epsilon moves are essentially free. I can go from 0, I could go immediately to 2, right? I can also go immediately to 1, I also could go immediately to 3, and I also could go immediately to 5. So when I process, say, the empty string, what should happen? What set of states should I get back? So if I give you delta hat of Q, so some state, and I give you epsilon. Previously, we had it where if you don't feed a symbol, it just stays in the same state, right? However, we have these epsilon moves, these epsilon transitions all over the place. But remember, those exist, right? So we have something a little bit different here. What should go on the right-hand side there? Somebody tell me. Don't be shy. Yes. So it would be E closure of 0, but notice that I'm just using Q here, so you just put Q right there. Perfect. So it would just be the epsilon closure of Q. Perfect. Wonderful. So that's the basis. So if you don't put a symbol in, you're just going to get the epsilon closure. So that's what differs. That's one thing that differs. The other thing, and this is the other difference between the NFA and the epsilon NFA, is that now when you transition from once on a set of states, right? Like I can go, I'm a whole bunch of states, right? I have a set of them. There's very much the same idea in play, but that I can also transition all those epsilon moves on that set of states, right? So I'm going to change my extended transition function for the epsilon NFA this time to include that. It needs to incorporate this. So I'm just going to give you a less formal definition first, and then I'll go formal. Less formally, after computing the set of states as in the NFA, like before, epsilon closure is applied to all the resulting states. So let me get a little bit formal about this. So really all I'm doing is I'm adding an extra step. That's all that's happening. So before I had this idea where I go from one set of states, I look at all of them, and then I transition on them. So I follow the arrows from that current state to all the states it can transition on that symbol. I do it over any ones that are currently active, as in like the ones I'm presently in. Sorry, I'm getting really excited about this. We just had to add this extra step that we're going to apply the epsilon closure to it. That's all I'm doing. So formally, I'm just going to say suppose W is equal to XA, where A is the last symbol of W, is the last symbol of W, and let, so I'm going to let, this is going to be very much like when I defined it for the NFA, just the normal plain vanilla NFA. Delta hat of Qx is going to be equal to a set of states, P1, P2, all the way up to Pk, period. I was about to make that a comma. I was getting a little excited, but this will be way too long. Then, this is how you're going to compute the whole string here. So I'm going to have delta hat of QW is equal to the epsilon closure of the union. So like I said, the informal way is a little easier to understand at first. Okay, I do the epsilon closure over all of those transitions given A. Here, I'll get out of the way. I'll get out of the way so you can see this. So the part that looks different is just this part where I apply the epsilon closure. This is exactly like I had before with the NFA. So that's the only thing that's different. So naturally, just because I have to do this, I have to describe the language of an epsilon NFA. So if I give you some epsilon NFA, I'm getting ahead of myself, when I defined the language for an NFA before, I had a very specific way I did it. I took the set of states and I performed an intersection with the set of final states, and I said if that's not empty, then we say that we can accept, right? Is there anything about my way I defined the epsilon NFA that changed with respect to that? Not really, no, because it's still essentially doing the same thing, right? The only thing I added was this feature where it has this epsilon closure happening. So let me just almost rewrite this out. I'm just going to change it up a little bit. Given epsilon NFA E equals Q sigma delta Q0 F. Then the language of the epsilon NFA, or language that the epsilon NFA recognizes, is strings W, such that delta hat Q0W intersect the set of final states is indeed not empty. Boom. So notice that I've already, so now we got sort of the hang of this. So there's an extended transition function. There's how I can use that extended transition function to define the language that machine can recognize. And now I have all the bits and pieces. I want to show you something that's really nice about the epsilon NFA. First, are we okay with this? Is everything fine here? Any questions? Because remember, this part's not really that much different really at all from when I did it with the NFA. Okay, I think we're good. I think we're good. So I want to proceed now to describe how we can convert an epsilon NFA to a DFA. Now, actually, let me stay over here. I'm going to use this board to describe the process, and then I'll go over there and we're going to do the example with whatever space I have left on the boards. I was getting a little excited there, and I was thinking, oh, well, I could do it over there, but I probably will need the space for our example. Gotta change the flow of things after all a little bit. So let's do this. So I'm going to show you that the subset construction, with a slight tweak to it, I can take an epsilon NFA and turn it into a DFA. Now you might ask, Dan, how do I go from an epsilon NFA to an NFA? Well, really all you have to do is you look at the NFA and then you say, okay, well, if I apply an epsilon closure on each one of the states, what I have to do is basically modify the NFA, so I add the edges in, which would correspond to the epsilon moves. So you look at the epsilon closure and you'd perform the transitions, as in you'd add them in by modifying the transition table. So if you see an epsilon closure allows you to go from another state that you haven't accounted for, then you better add it in as a transition that you get. But I'm not going to go into detail about that. I think in CISPR, or CIPSR, I have a hard time pronouncing S's and P's sometimes when they're put in a certain way. It's kind of strange. In the book there, they describe this process. So if you're curious about that, take a look in this book. I'm going to instead focus on how you go right from an epsilon NFA to a DFA because it's more practical in the sense. And also, if you really wanted to get an NFA, remember I showed you last day how you can convert a DFA to an NFA. Remember the wrapper, not the yo-yo, but I try to wrap it in the language of an NFA. So I just want to make that remark. So I'm going to describe how you can go from, so this is for if you want to know how to go from an epsilon NFA to an NFA. So I'm going to talk about how you take an epsilon NFA to DFA conversion. I'm sort of trying to build a big toolbox for you that's both theoretically interesting, but also rather practical. So naturally, we can employ a modified version of the, and I'm going to put in parentheses because you can still apply the whole subset construction to this idea, but we're going to use the lazy subset construction today, the one I showed you the other day. Why? Because I don't want to draw out the whole table, and it's so much easier to do it the lazy way. So let's see here. A lazy subset construction to build DFA D is equal to QD sigma delta D QD FD from an epsilon NFA E equals Q sigma delta E Q0 and FE. A lot of symbols. Jesus. So let's do this. So I got to describe, just like what I did last time when I did the subset construction stuff. I described to you how I did the states, the transitions, and so on. I'm going to describe that right now, and then we'll do an example. Since you have most of the bits and pieces from the subset construction, I'm going to go a little faster with this, because it's not really going to be that much different. It's one real step that really changes. So it's going to be a set of subsets, S, which is going to be a subset of QE, where we're going to end up with something called an epsilon closed set. And what the definition of that is as follows, where each S is equal to epsilon closure of S. So this is what we call sometimes an epsilon closed subset. What does closed mean in this sense? What I'm saying is if I give you the set, when I apply the epsilon closure to it, I get back S. That's all I'm saying. I must remark, just for the sake of completeness, that if I gave you the empty set is an it's an epsilon closed subset, or an epsilon closed set. So just as a remark, the main reason why, if you look back at the epsilon closure definition, if I give you no states, it's just going to be empty, right? So that means it's just an epsilon closed set. I must stress that QD can be built in the same way as I did with the lazy subset construction, but I'll put those details in the notes, but I'll just leave this here for now. But I'm just going to remark that we can discover all the states via the same lazy subset construction. But I put more details in the notes if you want to read a little bit more about this. For you guys, it's not going to be that much of a difference. The only thing that's going to be different is how we discover the new states. And you might guess what that change is going to be based on our definition of the extended transition function. Instead of doing final state, let's do the start state first. Again, I just really want to get to that transition part. It's kind of exciting. So the start state, you might guess quite quickly what that's going to end up being. Well, QD is just going to end up being, remember, just like in the subset construction, we're going to end up with labels that correspond to those subsets. So in this case, you're going to apply the epsilon closure on Q0. So that's what you're going to do to get the start state. You're just going to apply the epsilon closure. This should correspond to the definition I just gave you before. The final states. So if you want to get the final states, I'll write it more formally this time because last time it's essentially going to be the exact same here. So FD is just going to be the subsets S, where S is in QE. And the intersection of S and QE, sorry, FE, getting a little ahead of myself, FE is not empty. In plain language, if this looks a little cryptic, don't worry, it's literally the same as in the NFA. What this essentially is just saying that at least one of the states represented in that subset has to be one of the final states. That's all it's saying. So I just felt like writing it a little differently for you so you could see it written a bit more formally. But I assure you, this is exactly the same way we had it in the NFA. So now I want to talk about the transitions. So here, transitions. So this is the part that's going to be a bit different, besides the epsilon closure before. So I'm going to let there be a set S, or I have P1, P2, PK. Then I'm going to tell you that delta D SA. So I'm given a symbol A. So I'm reading a symbol given that state that's going to be represented by this set is computed as follows. So there's kind of two steps. That says follows. It's sort of melted there. So I'm going to write it over here. Let me just write it over here. I'm going to write these two steps down because we're going to use it a lot. And we have just enough time to do our example, which is perfect. Note, if you look at the notes when I post them later, I put another example of applying this process. I did it to the case where we had these, where I was reading the decimal numbers from last day. I did it to that epsilon NFA. I encourage you to try it with the other example with by yourself. Okay, so I'm going to get rid of. I'm going to write it way on to the right side, just so we have it on disposal, because we're going to use it quite a bit. Okay. So the first step is that we compute the union from I is equal to 1 to k. Remember, k is the index for which we had over here on the right board. So we have a set of states. And then I just apply for my transition on the epsilon NFA, pi on the symbol A, and I'm just going to let the result, remember this is going to give me a set of states, so I'm going to let it be called R1, R2, all the way to Rm. So I'm going to have this set that I get as a result of performing all these union operations with the transition function on the epsilon NFA. So I'm going to define delta D to be, for S, given symbol A, to be the epsilon closure of the set consisting of R1, R2, Rm. So this idea is no different than what I just told you earlier. I compute the transitions just like I did in the subset construction, exactly the same way. Except now I have the possibility of having where I have these weird transitions happen. Those are addressed by applying the epsilon closure on that set of states. So there's two steps instead of just one. You do this computation just like you do in the subset construction, except you add, after that you apply the epsilon closure to it. That's all you do. That's the only difference. So if you're familiar with the subset construction, like we did the other couple times, this is just going to be just one extra step built on it, just as I suggested the other day. So let's do an example. Let me just draw out a table, because we're going to need a table at some point here. So first, while I'm writing out this table, can somebody tell me what QD should be? So I'm going to do it on this example here. So what should QD be? What's the start state of my DFA? Well, it's the epsilon closure of the start state of the epsilon NFA, which is, it's 0, right? However, we have to apply the epsilon closure. We computed that earlier, right? So what is that? So we know it's 0 is in there. I think it was 1. Perfect, perfect. So this is our start state. And now what I'm going to do is I'm going to go through each one of these. So now, if you're wondering about the rationale behind all the calculations I'm doing, I've included them in the notes, but we're going to kind of do this, it's kind of a little bit more of a wavy way. So if you're wondering, Dan, when I'm doing this and it tells me to show work, like to what extent, like it's pretty open-ended, but I'll just remark that first we have to compute each one of these entries. And as we do this, we're going to discover possibly more states. So let me first begin with the first entry here. When I have an A, so if I'm at this state and I read an A, what should I do? Now remember, what I have right there, that's my set P. So sorry, not the set P. It's P1, P2, P all the way up to PK. So what I have to do is I need to apply the transition over each one of those states that's in those curly braces. I have to read the transition on symbol A, and then I'm going to apply the epsilon closure to the resulting set of states. Okay? So when I read off an A, and I'm in 0, what is that? What's that? Well, first, let me just write it out. So we know that if I'm reading this, it's going to end up being, it's going to be quite lengthy, so just please bear with me. So I'm writing out a little Foley this time so we can get an idea of what we're doing. Three and an A, and then I have 5. And I got to make sure I add my E's everywhere. Okay. So I think I have them all. I have them all here. So I have to compute the transitions on each one of these. Now, the great part is that, okay, there's no transition on A here. So, you know, this is going to be empty. So, you know, this is empty. That's empty. 1, I don't see an A anywhere, so that's empty. 2, I see an A. This, however, this is going to result in the state 4, right? How about 3? I don't see an A anywhere, right? So this is empty. So this is empty as well. How about 5? 5, I don't see an A anywhere on its transition, so this is also empty. So that's also empty. So you know the result when I take the union of all of these is going to be equal to 4. Sorry, the set containing 4. So let's write that down. Okay, we need to be careful. Did I get everything? So that's on just A. Did I get everything? I'm just trying to think for myself here. Okay, is it, let's see, 0? Okay, if I read an A, I'm pretty sure that's just it, I think. I think is it just 4 or do we have anything else? Yeah, I think it's just 4, I think. I think it's just 4. We'll come back to that one if we need to double check it. Or do we? So this is the calculation from here, but I'm not done right. What do I have to do to this? I have to apply the epsilon closure to this. So the epsilon closure of state 4 is what? It's 4 and, because look, there's a transition from 4 to 5, right? So it has to include 5 as well. So that's the extra step. So I must stress this. You need to remember to apply the epsilon closure to the result. That's the extra step you have to keep in mind when you're doing this. Does everybody see that? So that's the extra step. That's the only thing you need to remember beyond the start state and when we do this. Then the subset construction is going to basically be the exact same, except all we need to do is remember we have to apply the epsilon closure. If we make that mistake, it could pay big time when we're doing the example, because remember, we're discovering new states as we do this. Okay, let's look at B. I'm not going to do all the calculations like this before. I'm just going to go through each one and look at the transition. So this is why transition diagram, or even just the table, is easy enough to read off. That's why I usually like to include this, because it's a little easier to transcribe off of. Or if I want to follow my fingers, that also works pretty well. So I look at 0, and I read it. So which one? So I have 0, 1, 2, and I have 3 and 5. Now, these are all empty, except for this row, right? But that's for A. How about for B? Here's for B. 0, 1, 2, 3, and 5. Look at this. Look, I have 3 and 5. They both transition on B. Sorry, I have 3 right here. 3. I'm getting a little ahead of myself. Okay, I have 4 and 5 here, but those are on states 3 and 5. Exactly what I have in here, meaning that they're going to get included in the result of step 1, right? So I have to apply the epsilon closure to that. What is the epsilon closure of 4 and 5 in a set? Can somebody tell me? So 4 and 5. So if I give you the set containing 4 and 5 like this, and I apply the epsilon closure of that, what is that? What's the result of this? So remember, the epsilon closure contains each respective element in that set, right? At minimum. Because remember, the epsilon closure of a given state contains that state. So if it's 4 and 5, then it means it has to have 4 and 5 at least in it. So if we have 4 and 5, look, I have an epsilon edge that takes me from 4 to 5. So if I were to apply the epsilon closure on 4, I should get 4 and 5. If I apply the epsilon closure on 5, I should just get 5, right? So that means I'm just going to... So the fun thing is that the epsilon closure here didn't make any difference. But you have to be careful. So this is a new state. I've discovered this state, so I'm going to include it and a new row, just like I did with the lazy subset construction before. This does contain the state 5, which is a final state, so I'm going to make sure I indicate that. I look at A, look at 4 and 5. Okay, 4 on an A, there's no transition, right? on a 5 and I read an A, there's nothing, right? So I look at 5, 4, and 5, there's nothing there, right? So nothing. Then I take the epsilon closure of that, which is also nothing, right? So I end up with nothing. And then I consider the B. Notice that there's no B here leaving out, except for on state 5, I do have one, right? It's right here, the self loop. So I'm going to have just 5. Epsilon closure of 5 is just 5. Now, I want to show you just one quick way of drawing these epsilon NFAs. So I'm going to ignore the fact that there's an empty set right here. Normally when I do this, I add a row for this one, because it is, in fact, a new state. But I'm just going to proceed right to 5. I'll throw it in there. Let's throw it in there. I don't feel like deviating too much from things today. Okay, so epsilon, this is really easy. There's no way you're going to get anything interesting out of this. This is our dead state. And then I have the 5. This is one that I discovered right there. This contains the state 5, so I should make sure I include it. Well, there's no A leaving out of a 5, so you know that's going to be empty. The epsilon closure of that is just empty. And now I have the B case. Now remember, when I have a B here, it transitions from 5 to 5, right? But what's the epsilon closure of 5? It is just 5, right? So if you give me 1 minute, I could draw the transition diagram for you. And I have one last thing to summarize, and then I'll close things up for the day. So I apologize if I'm going a few minutes over here. I apologize for that. Hopefully that's fine with everybody, because I just want to put it in a nice bow for everybody. So let me just draw the transition diagram. So I'm gonna start. So I'm gonna label my states just like I have over there, 2, 3, 5. This is a start state, but notice it actually contains also the final state. So I better make sure I include a star there as well. Did everybody see that? So notice it contains 5. So that is technically a final state. Then I'm going to have a state for 5. So this is going to transition on A or B. And then I'm going to have a state. Now this also is a final state, right? It's also a final state. I have 5. Is 5 a final state? I'll let you think about that. And I'm going to also have my dead states. So somebody tell me, that's a final state, right? Is that a final state or no? I think it is, because it contains 5, right? So if I want to go from 4 to 5, notice that, 4, 5 to 5, I have to do it on a B. And on an A, I go to the dead state. So this is what we call a dead state. Then let's see. On the 5, I can go back to a 5 like this on B. And of course on 4, 5, 4, 5, I got accounted for empty. On the dead state, I need an A or B. It stays in the dead state. So this is what we call a dead state. I think I may have mentioned this before. This is a dead state. Oftentimes when you're drawing these transition diagrams, sometimes it gets very cumbersome to draw the dead state. So sometimes we refer to DFAs with dead states. I'll make one mention of it before I close out here. So I apologize for going a little longer here today. It'll all be in the video, obviously, if you have to go somewhere. So please don't let me push you. It'll also be in the notes, so don't worry. Okay, so let me just finalize this. So we have still a transition from 5 to the dead state, I think on an A. I think I've gotten all the transitions. I think we got everything. I think we're good. Does anybody see anything missing? I think we got everything. I like to do this stuff with everybody, so it's one of these fun things. I think I got everything. But yeah, no, so this is the process for which I can convert an epsilon NFA to a DFA. Now, I just want to make two remarks. I want to point out that there's often a convention where we talk about so-called DFAs with dead states. I have a section on this in the notes. It's a little brief description. Just talking briefly about this. But sometimes people refer to a DFA even if it doesn't actually define every transition. Because remember, in a DFA, the way we defined it, every single state has transitions on all the input symbols, right? So dead states. Sometimes it's very helpful to have this idea of a DFA with dead states. So what I mean by this, just to take that example, imagine if I didn't draw this state at all. You would agree with me that if you read this, you'd be like, okay, well, if there isn't a transition there, it better just reject, right? That's what you'd think would happen, right? So this is just simply a DFA where we do not include transitions that lead to a dead state. So in this course, I'm going to refer to these as DFAs with dead states. So if I tell you, draw me a DFA with dead states, what I'm saying is don't include the dead state in the picture. That's all I'm saying. So you would just pretend this doesn't exist, and you would just proceed with drawing the transition diagram. It makes it easier and less cluttered when you're dealing with more complicated examples. So one question I do have for you is, when I do that, when I don't include the dead state in my transition table or in my transition diagram, is it still technically a DFA or is it something else? Yeah, so it isn't anymore a DFA, it's now an NFA. It's technically an NFA. So I must stress that even when some people say, oh, I'm going to define it so that you don't have this here anymore, notice that now you have it where transitions can go nowhere, right? So when you remove that row, say if I didn't have this row in my DFA at all, you're technically defining an NFA, right? So this is technically an NFA. This is technically an NFA. So just keep that in mind. When somebody tells you, oh, we're looking at a DFA and it's missing some transitions, they're technically describing to you an NFA, but conventionally it's easy enough to just tell you, oh yeah, all I'm doing is I'm adding a dead state in here. And you might ask, Dan, why would you say that? Well, if you use the subset construction on the NFA that looks like this, where you remove that row for the dead state, it will actually add it in. So if I look at the NFA and I perform the subset construction, just like what I did just a moment ago here, if I didn't include that state, it will get actually added back in if I do the subset construction, which is an interesting property of the subset construction. One of the examples I have in the notes actually does produce one of these dead states. So if you were to actually get rid of it and then interpret it as an NFA, then apply the subset construction again, you would actually get back the dead state, which is kind of an interesting thing to think about. One last thing I just want to remark. I read it more formally in the notes, but I must stress, remember, I just described to you a process that takes any epsilon NFA and turns it into a DFA. You can use the same types of arguments I gave you from converting from a DFA to an NFA for a DFA to be converted to an epsilon NFA. So, believe it or not, the same connection exists between the DFAs and the NFAs as there are for the DFAs to the epsilon NFAs. So there's actually a connection between all three. What is the connection? What languages do they accept, everybody? Starts with an R. I'll start. What do they accept? What kind of languages? Don't be shy. What kind of languages do all of these machines recognize? Has a name. Starts with an R. Regular languages, perfect. So all of these except regular languages. That's the big thing. Isn't that powerful? So that means that all of these are different ways we can look at how we can describe regular languages. So when we come back next time on Monday, what we'll do is we'll see a way we can actually describe in more of a declarative way regular languages, so-called regular expressions. So when we'll come back, we'll see that. So I want to say thank you very much, and thank you for being patient with me. I really appreciate it. So have yourself a beautiful day. I'll see you later.